then let's see here. So the plane down here is, well, something like, I have a hard time drawing a plane. Let's make it a flying car. There we go. Okay, so the flying car here is going like this. And then up at the top, the flying car, through its magic, I don't know, there you go. It's going the other way, right? So here's, let's say, V1, here's V2. So we know that the net force on the car has to be what, like? Oh, excuse me. We don't know about the net force. What we know about is we know that if it's going in a circle, we know that there's part of the force has to be. How can I say this? The force could be like this. The net force could be like that. That's possible. All right, but this component of it, that's not up for grabs. If it's going in a circle, this component has to be mv2 squared over r, where that's the radius of the motion. That part of the force, the center-seeking part, has to match that by calculus. Now there's another piece over here, the tangential part of the force, right? And that's another story. That would go towards tangential acceleration of the motion, right? It could be speeding up. It's going on the top, but it's speeding up in its speed around the circle as it's going through that top, right? Then that would be like that. On the other hand, if the net force vector pointed over this direction, then the tangential acceleration would be negative. It actually would be slowing. The speed would be slowing while still going in a circle. But to go in a circle, you have to have that center-seeking force mv squared over r. And so where's that coming from? What's supplying that? The fact that it's this is just kinematics. It's calculus. Where's that force coming from? That's the question. Well, I suppose the one place the force could be coming from would be what? So the force of magic, the magic force, engines, a flying car, right? Or for the plane, it's the lift force, the aerodynamics of the air pushing on the wings, other lift surfaces and such. But then there's something else that's easier to understand, right? We're on near the surface of the Earth. Gravity, right, yes. So something like that. Now that's just for the whole body. Now, how can I say this? Now, in the problem we were looking at, it was given that he's weightless. But the thing that I'm still having trouble thinking through. He asks about his apparent weight. So how would where does apparent weight enter into all this? In the elevator example, it was easy to think about, right? So you have a scale, right? You got some guy standing on the scale, right? And so because in the frame of the elevator, right, you can look at the problem in the frame of the elevator, and in the elevator frame, what are the forces? Well, you got mg down, right? You got the normal force back up, and also in particular, if you study Mr. Top Hat here in the scale, he's putting a contact force down like that, right? But then the scale is pushing back up on him with that contact force, and that's what we call the normal force, right? The normal force is the reverse. It's the third law pair of the contact force his feet put on the scale, and conversely, the floor, in this case, the scale puts that contact force back on him, which by the way is the normal force. All right. So the apparent weight, right, is based on that normal force here. Now that doesn't have to be this doesn't have to be. These don't have to be equal though, right? If this is an accelerated frame, we had ma is equal to what? Did we say a was up or down? I don't know. You pick it. What do you guys want? A up or down? Positive. Up positive, all right. So then we've got normal force minus mg, right? But this normal force is really the apparent weight, right? That's a better example to think about apparent weight, I think, to get started. For example, if the elevator is free falling, his apparent weight is
0.
Yes, 0. And on the other hand, if the elevator is going at constant velocity motion, much like the ones in our building, then you have an apparent weight of your weight. A is equal to 0, n is equal to mg. Somebody move these boards. No, sorry. I've been shopping for chalkboards. They're rather expensive. Yeah, I want a chalkboard. Why not? You ever watch a video from, like, I don't know, pick any of those silly schools that at some point in their life have been unaccredited, like Harvard or MIT. And what you'll see is lecture after lecture in front of these things called chalkboards, because those are universities, and that's what you do math on. Sorry. I have a certain opinion on this. These whiteboards were here when I got here. The battle was lost before I even came here. It's interesting, in a math department where there's like a male-female divide, like if you have male faculty and female faculty, what I've heard is that, like, the female faculty prefer whiteboards and the male faculty prefer chalkboards, and it's like a sexist thing. It's interesting. I don't know, it's very interesting. I'm not sure why that is. Fun. That has little to do with your class. I'm sorry. So to think about apparent weight, this equation, where is this equation? This equation is written from the rest frame of Earth. So if you could affix, a coordinate system on this board, this equation is happening in that. To understand apparent weight, you have to imagine yourself in the flying car and think about the frame of reference that's moving, co-moving with that, to really understand the apparent weight, right? So like down here, if you can imagine yourself in here, what do you have? You've got, think about Mr. Top Hat standing on the thing. What's happening? He's got what? He's got mg down, right? And he's got the normal force of the car on his feet or whatever back up. And that's all equal to, and so you've got like what? But you have so you have mv squared over r, and that's the ma for this. It's a moving frame, right? Sorry, and n is upward, so that's n. And then you have minus mg. So that's why if this worked out to say be 2,000 newtons, okay, and if this happened to work out to be 500 newtons, then the apparent weight at the bottom would be 1,500 newtons. 2,500 newtons, right? Yeah.
So the mv squared over r is the centripetal force going towards the center of the circle? Acting on the car.
Yes. Although technically speaking, it's not really a force. I mean, we say it's a force, but it's not really a force because it's just a kinematic term that comes from the fact that it's going in a circle and you do calculus, and ma has to work out to be this. So, I mean, philosophically, this is not a force, whereas these are. That's Newton's second law. Ma is equal to F, right? These things are equal, but they're not the same, philosophically. It's kind of a subtle point. At the top, on the other hand, if you look at it and you think about the guy in, Mr. Top Hat standing here, all right, what's going on? Well, in this case, that's mg, right? And that's also the normal force of his feet. The car is pushing on his feet that way. the situation's turned over, right? So in this case, you've got what? You've got mv squared over r is equal to n plus mg. These are both center seeking. Okay? So what does that mean? That means that the apparent weight, which is the normal force, by the way. And so what did I tell you guys last time? At the top you do what? At the top you subtract the weight, right? At the bottom you add the weight to get the apparent. So in short, I mean, what we're deriving here is to find the apparent weight, you take, you calculate mv squared over r, and you add mg if you're at the bottom, whereas you subtract mg if you're at the top to find the apparent weight, the normal force. Now, if you just stop and take a second and think back about this, this makes a lot of sense. If you've ever been on a Ferris wheel, right? If you experienced this at the top, you kind of feel like, right? Because you have that the sensation of weightlessness. It's not usually quite weightless, but you feel lighter at the top, right? And then you go around and you come back down, and then all of a sudden you're pressing on your seat at the bottom, right? And so that's why that happens. The normal force is where we get that feeling of weight. So, sorry, I didn't say that last time, but my ability to think is directly proportional to whether or not that fan is on. All right, with that, do you guys have any questions? Should I start at the end and work back? So what's on the test next Tuesday? What's that? Stuff. Seems safe to say. We haven't covered the physics of not stuff yet, so. Here, I'll start with the last problem in the last homework. How about that? And we'll work our way back. Number 14 of homework 5. Now, there's various ways to make this problem simpler. Would you like me to work with a simpler version of this problem to start with? So here's a simple twist on it. If I have a pulley here, if I have a mass m1, and then I've got a string which does not stretch and has no mass, and also this pulley is massless. It's very magical. But for our convenience of math and such, we assume that. Then the question, of course, is just what's the acceleration of such a system? So how would we solve this? Well, there's two things to think about, right? Mass 1 and mass 2. So mass 2, if you look at that, we've got m2g going down, right? And we've got the tension force T going up. Now, again, this is a massless pulley, and the rope is massless, and it cannot stretch. And what that means is that the tension, one of the things it means is the tension is the same in the whole thing. So there's that. This one, also, we've got a tension force T, the same tension, going that way. So pulleys are kind of cool things. They change the direction of the tension. You're like, wait a minute, I thought the tension was going that way. How can it also be going that way? Well, remember, tension's a concept. It's not that this and this tension are the same actual force. What we're actually saying is there's a string, right? And the string pulls on the one box up, right? But it pulls on the other box that way, right? I mean, just think about it from common sense. Could the tension point that way? No. I mean, if some of you happen to have a rope, we could try to get a rope out and try to push a box across the room with a rope, but I don't think it would work. Oh, and are there any other forces at play? Oh, of course, our old friend M1G is here. Right? And then what? Yeah, and the normal force.
The frictionless table?
Yeah, frictionless table at the moment. Of course, we could add friction if you'd like.
No.
Okay. And so we write down Newton's laws. And so, for example, for M1, the vertical, we've got 0. Why is it 0 in the vertical direction? Yeah, true. What else, though? It's staying on the table, right? So the vertical acceleration 0, right? Stays on the table. How about horizontal? There we have ma is equal to what? T, right? If we did have friction, we would say minus the force of friction here, right? And then how about M2? Yeah, there's no really horizontal to think about, so I'll just get straight to the point here. M2A is equal to what? Right, now why did you say M2G minus T, not the other way around? You don't know. Look at the picture, right? A going down is positive, since we said that that's our definition, right? So if I put a plus on the T here, that forces me to put a minus in the other one. Or vice versa. You could redefine A to go the other way. All right, then what do you do? Add these equations. I'm sorry, this should have been an M1, right? Add these equations, you get M1 plus M2 times A is equal to M2G. And so, consequently, we get the acceleration is M2 divided by M1 plus M2 times G. There you go.
Professor,
Yeah.
say that again, why you said it's M2G minus 2?
Well, once I define this to be the positive direction, that means that T is going in the same direction here, right? On the other hand, I have to follow that along. Here's the same rope, right? So making this the positive direction makes down the positive direction, consequently over here. So T is the opposite. It says minus. Here's a problem I never put on a test yet. It's very unsettling.
I'm guessing the keyword on yet.
What's that?
I'm guessing the keyword is yet.
Yeah, I mean, I don't know why I didn't. I could have. I usually add friction to this problem. It occurs to me, though, I could add an angle. Like that. How does that change things?
Just the components of M1
What's that?
and the normal force changes a little bit.
Right. So I'll make A the same, right? And I think the story for M2 is not any different, right? We still have tension and M2G down like that, right? So same song and dance, we get tension is equal to M. Did I say? Wait a minute, you guys don't, what did you guys let me, you guys got to stop me. I've switched the meaning of 1 and 2 in the previous example. Come on, guys, you got to stop me. Look at this. M1, right? I've got vertical and horizontal for M1, right? And that's fine. Oh, wait a minute, no. M2, okay, that's fine. What is it? What am I doing? Where's the wrongness? Oh, never mind. If you're confused, that's good. There was nothing wrong. Okay, good. Sorry. Physics is susceptible to user error. What can I tell you? Now, this, on the other hand, is more fun. See, because now I have to think about the normal force is like this, right? Part of gravity goes like this. Another part of gravity goes like that, right? So gravity, mg, m1g to be more specific, has two pieces. It's got this piece that's parallel to the plane, and it's got this piece which is perpendicular to the plane. Where do I put theta in that green triangle I just drew? The same theta.
Vertically
Oh,
straight
there's-
down from the dot of M1.
So like
The angle between-
this one?
I can't see it.
Sorry.
Yes. Wait, what?
The opposite?
Yes.
Oh, this one? Okay, we can't have both. Let's see, that would make this mg sine theta, and that would make this one mg cosine theta, right? Those are the components of the gravity force, the parallel part and the perpendicular part. You guys with me? Okay.
That little vector that you like pulled out, where you just said where the theta would be, where is that section on the drawing?
Fair question. This is that. This is that.
Okay.
I just decided to try to illustrate it separately because it's,
Yeah.
yeah.
Couldn't you do it by just drawing a perpendicular straight down line from the dot, and then isn't it the angle between?
Yeah, sure. Yeah, you could do it other ways. I just want to emphasize that we're just splitting gravity into two pieces, the part which is perpendicular and the part which is parallel. But both of those arrows go together to make the force of gravity down. Okay, now we go back to Newton's laws. It's a little bit more exciting this time. M1, we got vertical. What do we got vertical? Still 0. I mean, and when I say vertical, I don't mean vertical anymore. I mean perpendicular. The perpendicular equation. Perpendicular, we got 0 because it's not accelerating into or out of the inclined plane. We have 0 is equal to the normal force minus mg cosine theta. All right. And how about the parallel direction? By our definition, ma, right, equals, oh, I forgot something. Oh my goodness. Shame on me. It's not just sliding down the plane, it's being pulled down the plane by the other box, right? There is this guy right here, the tension. Don't forget about the tension, it's also there, right? Pulling down. So ma is equal to tension minus mg sine theta, right? Oh, that's a good question. The answer is I wasn't done. There you go. Okay, that's not the real answer, but I'm sticking with it. Let's see here. I was just going to let class out when the fan turned on, but it seems a little premature. All right. The other one I've got for M2, I've got, oh, M, what is M? M is me being lazy. Don't do that. If there's two masses involved, don't use yet another symbol which is ambiguous. These all should have what on them? Yes, the subscript matters. If you don't put the subscript on your work, I don't know what you're doing. And, you know, I would like to be a glass half full kind of guy and just say, oh, you must be right. It must have the right meaning. But I've just graded too many physics tests, and I'm not allowed that luxury. Because unfortunately, many times, the student is not right. I want you guys to be right. Please be right. Don't make mistakes. Could you guys do that for me? Don't make mistakes on the test this time. Everyone gets 100. But by that I mean, like, take the test, you do everything correctly. And I look at it and I just get bored with the grading. I'm like, oh, another one of the same solution. Won't somebody finally make a mistake in this class? Would you guys do that? No?
We'll try our best.
You try your best? Okay. Well, I'd appreciate that. Oh, then we can solve. We do the same thing we do every time. Add the equations. What do we get? M1 plus M2 times A is equal to
M2G plus MG sine theta. M1.
Oh, yeah, I'm sorry. Thank you. I'm not thinking clearly. No surprise there. Let's see, mg sine mg1 m1g sine theta. All right, fine. Acceleration then. m2g. I'm going to factor out the g. We got m2g, m2 plus m1 sine theta, all divided by m1 plus m2 times g. This is still not really that homework problem I started with. These are examples like that, though. Does this make sense? If you compare this result, right, to that one, see how they compare? This really should have the first example as a special subcase, right? Does it? What happens if we put theta equal to 0? How about theta equals 90 degrees? Free fall, right? That make sense? It does, yeah. Your actual homework problem is something more insidious. It's something like you've got theta 1 here, but you got theta 2 over here, and they're not equal. They're not equal. And so in mine, one is 30 degrees and one is 53.1 degrees. I'll even put in the numbers for you. 30 degrees, 51 degrees. Oh, I'm sorry. Yeah, 53.1. Hey, wait a minute. Do we all have the same problem? Well, that seems kind of lousy. This isn't randomized? How dare they?
No, it is. You just said it earlier.
Oh. Well, I think other things in the problem are randomized. And then, so what they do, this instrument of torture for physics students, the dreaded pulley. They put it up there, and then they put one box here, and put another box here, like so. Connect them with a string which is massless, all right? And for me, I've got M1 here and M2 there. What's the question ask? So M1 is 102 kilograms. M2 for me is 53 kilograms. He says, assume positive accelerations to be up and to the right for the left-hand block, and down and to the right for the right-hand block. In other words, he's saying, like this is the acceleration, all right, in terms of my diagrammatics. So then the question is simply, which way does the system slide when it's released from rest? And what's the magnitude of the acceleration on the blocks? And then finally, what's the tension in the cord? No friction. I mean, we could add friction to it if you'd like. So how do we solve this problem? Same way as those two. What you do is you draw the free body diagram on each one of these. So this one, we're going to have, let's say N1 like that. I'm going to have the tension going up like this. Part of gravity goes down like that. The other part of gravity goes like this. So it's just convenient for me to just go ahead and decompose the gravity in the free body diagram. I find it convenient personally. As we've talked about, the perpendicular one is m1 g cosine 30 degrees, whereas this parallel one will be m1 g sine 30 degrees for the usual geometric reasons. So if you look at m1 perpendicularly, not actually a word, and yet you knew what I meant, n1, weird how that is, n1 minus m1g cosine of 30 degrees. So that's Newton's second law in the perpendicular sense for m1, right? Again, m1 is not accelerating into or off of the inclined plane. You guys with me? How about the parallel direction? M1A equals what? I heard a T and a minus what? M1G sine 30. Okay. All right. You can't solve this problem one mass at a time. You have to solve it both masses at once, right? These masses are coupled. Their motions are coupled, just like this last problem we worked. You can't just focus on one piece or the other and write down a formula and have the answer. It doesn't work that way. You have to think through the concepts. You have to treat the system collectively as a whole. You have to apply physical law one step at a time. Same thing here. Oops, wrong color. I feel like the forces on this one are green. Let's see here. So we have a N2, like so. Tension, back up that way. And then you got, not the scale, obviously. I'm just drawing it for my convenience to be longer. So this one is M2G cosine of 53.1 degrees, whereas that one would be M2G sine of 53.1 degrees. Now that we've drawn the free body diagram and illustrated all the forces, I can put together Newton's second law, which is what here? So for M2, the perpendicular direction is kind of boring, or as my son would say, boring. N2 minus M2 G cosine of 53.1 degrees. And on the other hand, the parallel direction, we get M2A equals, now I gotta be careful. The tension this time is doing what? It's opposite, right? So it's minus T plus M2G sine of 53.1 degrees. Oops. Degrees. My goal is to find the acceleration, right? So let's call this equation 1. Let's call this guy equation 2. So if we look at equation 1 plus equation 2, what do we get? The tensions cancel, and we get M2 sine of 53.1 degrees minus M1 sine of 30 degrees, big parentheses, factor out a G, right? If you'll allow me this, fine, I can write So A is equal to m2 sine of 53.1 degrees minus m1 sine of 30 degrees, all divided by m1 plus m2, parentheses, g. And of course, you can crunch the numbers at this point, right? You can put the 102 in, you can put the 53 in. Sine of 30 is a half. You notice that the numerator and the denominator of that fraction are both kilograms, so the kilograms cancel. And then you multiply by 9.8. Sorry, this is a WebAssign problem. We're not allowed to put it to 10 just yet. Meters per second squared. And when you crunch those numbers, I do believe you will get 0.545 meters per second squared. And there you have it. Why don't I put numbers in earlier? Right. Right. See, if I solve this problem algebraically, I haven't solved just this problem. I've solved infinitely many problems of the same type. And also, it allows me to think about cases, right? If I don't put in the value of theta, if I keep theta as a variable, rather than giving you a specific numerical theta, then I have the freedom to think about what happens when theta is 0 or theta is 90 degrees, stuff like that. I'd almost rather have the problem with theta 1 and theta 2 here and think through it, you know? Then I could think about different cases and what happens and such. For example, if these are both 90 degrees, we should be back to the thing I worked last class, with just a pulley with the two things hanging off both sides, right? You can kind of see that happening, right? If these are both 90 degrees, you get m2 minus m1 over m1 plus m2, which is what we found yesterday. The other yesterday, you know what I mean. Yes, sir.
The acceleration be negative?
No. Oh. It might be.
Yeah.
You guys got a minus? Cool. Why is the answer still not with a minus? It's because of what the book, you gotta be careful of the wording. So what they said here is, what is the magnitude of the acceleration of the blocks? So that's their way of saying, we're going to be lazy about which way is positive and which way is negative. Even though they've got this really careful preamble to the thing, very carefully telling you which direction's positive and negative, they don't follow up on that by insisting on a sign-sensitive answer for the acceleration. Stupid. That's stupid. Sorry. Yeah, it says, what's the tension in the cord? Oh yeah, I mean, I would like for us to understand the sign of it, absolutely. What's the easiest way to find the tension now that we know that? Yeah, just pick any, the sign. I like equation 1. 1 tells me that the tension is equal to m1a plus m1g sine 30, which is, what was m1? 102 times a, which was minus, you're absolutely right. If I have the wrong sign here, it will make it wrong, right? Minus 5.45 plus 4.9, and this is meters per second squared times kilograms. This is a Newton, so whatever that is. Apparently it's 444 newtons, give or take. Seems right, yeah. If you had the sign wrong, you'd end up with like 530 some odd newtons. But. All right, so you guys got questions? I mean, Yes, sir.
Can you do the one where you throw something off a building and it says how much, like listen for it?
Yeah.
I think it's number 7, 8, lesson 2.
I will find it.
Yeah, some homework too.
Subway trains, fleas, motorcycles. Oh, yeah. A physics student with too much free time drops a watermelon from the roof of a building. Is this one?
Yeah.
Okay. See, to me, like, this, if it was just up to me, this is all we would do for physics lab. Be like, what's the budget for this year? I'd be like, I don't know. Tell me what the price of the watermelons this semester, and then I can tell you the price of physics lab. And that's all we do. Every day we just take a watermelon and find out a different way to destroy it. What's that? I'm not in charge. Insurance. The watermelon lobby. I don't know. You know about the watermelon lobby, right? No? Okay. I won't tell you about it then. Let's see here. W. What do you think the W in George W is for? It's watermelon. It's watermelon. It's part of the conspiracy. Let's see here. So you got a watermelon. It falls off the edge of the roof and falls past. Oh man, sorry. I've drifted into the world of problem 11 without thinking. Sorry. Focus. Physics student with too much free time spends watermelon from the roof of the building. He hears the sound of the watermelon going splat. 2.34 seconds later. How high is the building? Speed of sound is 340 meters per second. Okay, so I think sometimes for this kind of problem it's helpful to draw maybe 3 things. I mean, I don't know, I find this helpful sometimes. So to start with, you have the watermelon drops. This would be t equals to 0. And then here we go, splat. This is t equals to, say, t1. All right? And then so finally the sound reaches back at t equals to t2, right? So what we were given is that this t2 is what? We're given the total time it takes. We're not actually given the time that the watermelon hits the ground. That's unknown, right?
I thought it was T1 plus
Well, it depends on whether we're talking about absolute time or whether we're talking about durations. I'm talking about this like, that's 1 o'clock and this is 2 o'clock. You're thinking like, it took 1 hour to get here, it took another hour to get there. That's fine. You can go either way. Yeah. Are you going to talk about the moment in time, or are you going to talk about durations of time is the question. Okay, so what we have is y is equal to 1/2 g t1 squared. That's the height of the building. Why is that true?
No initial velocity.
Right, no initial velocity, just plain old kinematics, 1/2 gt1 squared has to be the height because that's the time it took for it to drop. Yep.
Isn't the total time 3.4?
Where did I get that 2.34 number from? It says 2.34 in here. Where did I get the 3.4 from? As I was warning, user error, 2.34, that's what's given for me. I had it right up here. How did I? These are the mysterious things. All right. Everybody with me here? I mean, the height of the building. I can be more methodical here. Y is equal to h minus 1/2 gt squared. So at t equals to t1, we have 0 is equal to h minus 1/2 gt1 squared. Therefore, the height of the building is 1/2 gt1 squared. There's the derivation of this from the basic kinematic equations that I stated and proved for you the other day. Then what? Going from here to here, what's the equation for the sound? The position y is just equal to the velocity of sound times time, right? I guess you could say t minus t2. Y is equal to 0 when t is equal to t2. Anyway, we also have h, getting to the point here, we have h is equal to 340 meters per second times what? Not t2, but in my notation, t minus t2. Yeah, well, excuse me, t2 minus t1, right? How did I? I'm sorry, this is still. This is a T1, I'm an idiot. T1. Right, because the sound starts at time equal to T1, splat, and then it travels up. So at t equals to T1, y should be equals to 0. This is the y for the sound wave. The sound wave is at y equals to 0 when t is equal to T1, the moment of the splat, and then it goes up with constant velocity of the sound, like that. And so when you get to time 2, which is when it reaches the top of the building, we would have the height of the building is equal to 340 times T2 minus T1. I don't insist you use my notation and my ideas. I just insist you get the right answer here. There's other ways to package the steps here. All right. So then what? Oh, we know that T2 is what? Sorry. Where did that 5 come from? Good grief. 340 times 2.34 minus T1 is equal to h. Oh, you said set them equal? Yeah, that's equal to 4.9 T1 squared, right? At which point, quadratic equation, we're done. I mean, we're not done yet, but. So I rewrite that in standard form and go to town. Let's see here. So I got 4.9 T1 squared plus 340 T1 minus 2.34 times 340 equals to 0. And that's a quadratic equation. I can solve it, right? This is not a pretty factoring problem. This is an ugly numerical problem. It gives me no joy to solve this. I will feed it to my quadratic solver. Let's see here. Mode, equation, 3, coefficient, 4.9. Coefficient of B, 340. Can you somebody tell me what 2.34 times 340 is? What's this?
795.6.
minus 795.6. All right. And so from the quadratic equation, we get T1 is equal to either 2.26 6 seconds, or T1 is equal to minus 71.6, well, 7 seconds. One of these one of these solutions, of course, is extraneous. I sometimes tell people that if I was to be a rapper, I would go by the name extraneous G. I'm not even in the solution set. Let's see here. Fun fact. So there you go. Oh, is that the answer? No, not really. What am I trying to find?
The height.
Oh, yeah.
Yeah, if you just plug that into the first height rate.
All right. So H then is equal to 4.9 times 2.266 quantity squared. That is going to give me meters. I got to get out of this mode. All right. You just told me 2.266 squared times 4.9 is equal to? That's a 2.2. That's not a 22. 2.2. So I got 25.16 if I haven't done something wrong. Yeah, I have 25.2 in the answer key. Get out of here. No, because I have 4.9. Oh. Yeah. No. Yeah, talk me in. You fished me in there for a second, but let me fish myself back out. Here, look at this one, minus 340 when you multiply it by the T1. That gives me a minus 340. So when I move it to the other side, it's plus 340. Conversely, this is a plus, but when I move it to the other side, it becomes a minus, right? Next. Or not, I don't know. This fan is removing my life force slowly but surely. Yes, sir.
There was one about shooting his gun overseas very brilliant.
You guys are killing me. There are numbers to these problems.
That was homework too.
Was homework too?
Dang, 3. Maybe it's 3. I don't know. I just know it.
Something about the sea. Was there a picture on it or something? Sea of Tranquility, huh?
Pretty sure it's not a number 3.
Homework 3, number 2. Oh, okay, I see. What do you think the first question on your test is going to look like? What is it? Did you say solving a logarithm? I'm just hearing what I want to hear, huh? I don't want to grade that. No. I don't want to find out whether or not you guys can solve logarithms. I have no interest in that. What's that? Running over a cat? No. Almost certainly the first question on your test is, here's 2 vectors, do stuff with it. Find the standard angle, find the dot product, find the angle between the vectors, calculate the cross product of the vectors, right? If I had to guess, the next problem is probably something like, here's 3 vectors. find the magnitude and standard angle of the resultant of like 2 times a plus 3 times b minus c or something. So I would guess it would start with vector algebra, right? Then there should be a question on kinematics, maybe with calculus, like here's the acceleration as a function of time, find the position and velocity. Then I would expect there's some kind of projectile motion problem, right? Here's a cat, it's on top of a building, you give it a kick at 30 degrees. It gives it an initial velocity of 20 meters per second. If you hear the cat splat, no. I know, there should be a kinematics question, right? And then there should be a couple of force questions, something like that. So, just to give you a feeling.
Due to the time, are physics exams usually not as high in quantity of problems?
I don't know. A pistol that fires a signal flare gives an initial muzzle speed of 110 meters per second.
This is from homework 3, right? That's homework 3, right?
Homework 3, number 2? Yeah. So the initial speed is 110 meters per second. And the part A is it's fired at an angle of 60 degrees above the horizontal on the level C flats of Utah. What's its horizontal range? Oh man, this is a gift. See, I could ask 30 of these questions, right? I mean, so I don't know how to answer that question. It kind of depends on how many easy questions I decide to put on the test versus how many legitimate questions I decide to put on the test.
What would you consider legitimate questions?
The ones I erased.
Oh, okay.
So, I mean, ones that actually require physical analysis that aren't just like plug and chug. I mean, this is a made to order problem. We derived this before. We proved that the range was v naught squared sine of 2 theta over g. This is exactly the situation where that formula is relevant because the initial and final heights are the same, right? So I can just use the range formula here. I guess the real question you guys should ask is, am I going to do multiple choice or not?
Are you?
I don't know.
Can you?
I could.
Are you going to do true and false? Like just the cat died, true and false.
See, my brother's invented a new question type. You may not even be aware of this question type. It's called true, false, or possible.
It does.
The rules of true, false, possible are, if it's categorically true, you circle true. If it's categorically false, you circle false. However, if there are qualifiers which make it true but not always, you say possible and you include the qualifiers which make it possible.
Like short answers.
It's so much worse than true, false. My brother pretends to be nicer than I am, but he's the one who invented true, possible, false. I think we know who's the meaner. Oh, radian measure. Well, that won't help anyone. Let's see here. 110 squared. By the way, I want numbers. It's important you have a working calculator and you know how to work it. That's part of this course. If you give me answers which are not simplified, I will take off points because I take no joy in punching a calculator to find out your actual answer. You do the work. Don't make me do the work. All right, sorry. 1069. I mean, this is not a physics course. This is. Excuse me. That was wrong. This is not a math course. If your answer is like square root of 3 over the square root of 13 or something, like that's not the answer. The answer should be like a decimal. Now, you say that's